Hi guys, this is EasyElimu channel. I'm Vincent Kanumwai. I'll be your teacher for today. I'm going to take you through Form 4 mathematics, that is area approximation. Stay tuned. Welcome. First, if we may look at the introduction of this area approximation, we can see that in Form 1 we learned about how we can approximate areas of irregular objects, and this was through setting it into a unit grid squares, and then from there we used it by counting the number of square where the area was covered. In this section we are going to use different kinds of method, an additional one like using Trapezium rule and also Ordinate Rule. We shall see how it works while continuing with the session. Stay tuned, welcome, and see how we do work it. On additional of Form 1 work, we can now view that we can still approximate a given area of an irregular shaped object or an irregular where you cannot use the actual measurement which we already know of regular objects like triangles, rectangles. I mean, when like you are being asked an irregular stone, for example, the area of this, the area of that figure. If you have been asked to find the area of that figure, you can find the area of that figure using several ways or several methods, and that is, you can use that of Form 1, or if it is an object drawn to a paper, the first thing you should take a paper, place it on the drawn object. If it is irregular in this form, you place the paper on top of it. If you have the paper, you open the paper and then you place on it, you trace the area, then you transfer it to one square grid where it has been well ruled with 1 centimeter squared, and then from there you identify the given scale. For instance, you may be given this land, this figure to represent a given land of a scale 1 to 50,000. This normally means that if you have 1 centimeter on the paper, 1 centimeter on the paper, given a scale of 1 to 50,000, it means that having 1 centimeter on the paper represent 50,000 centimeters on actual ground. And actual ground is on the earth's surface. For instance, if this one is the area of a given surface on the earth, so, and you have been asked to find the area of this given object. So what you will only do is that you will trace this figure as it is, then you transfer it to one full paper which has been well ruled with 1 centimeter square, and then from there you will now calculate. For instance, let's say that on transferring to our paper, we found that if we transfer to our paper, we are getting that it will be in form of this scale. Assuming that, if we assume that these boxes are 1 centimeter each, 1 square centimeter each, then we can say that the number of boxes we have, full boxes we count, we shall find first, count the full boxes or full grids or boxes. We shall find it is, you start by 1, 2, 3, 4, 5, 6, 7, 8, 9, and they are over. So we find that the total number of full boxes is 9 square squares centimeters, of which we can shorten it as is 9 square centimeters, because 1 is square centimeter. So we now count the half ones, and we treat each half even as little as they are. We treat each of the incomplete box as halves. For instance, here we shall treat this one as 1, 2, 3, 5, 6, 7, no matter how small it is, 8, 9, 10, 11, 12, 13, 14, even here 15. Then we move this one 16, 17, this box is 18, 19, 20, 21, 22, 23. So we are finding the number of incomplete squares is 23. So we also count incomplete. They are equal to 23. After finding the number of incomplete, we take each incomplete square to be like a half. So meaning if you need to get a full, you divide by 2. And if you divide by 2, we are going to get 11.5 full squares. So we shall find it is 11.5 square centimeter. Now the next process, or the next thing to do, we shall add the 2, and on addition of the 2 we are going to get, if we add, we get 20.5 square centimeter. Now we find, using what we have been provided here, we are getting that the area of that given figure is 20.5 square centimeter. Now the area here is 20.5 square centimeter. But remember, we were informed that 1 centimeter on the paper represents 50,000 centimeter on the actual ground. What does that mean? We can find it in other way. We know very well that 100,000 centimeters is equivalent to 1 full kilometer. And here we have 50,000. What about 50,000 centimeters? We shall find it is equivalent to 0.5 kilometers. So meaning that 1 centimeter on the ground, 1 centimeter on the paper represent 0.5 kilometers on the actual ground. So what that implies, if we have the area in centimeter square, then it means if we square this one, we should also square this one and find out that 1 square centimeter is representing, or on the paper represents, 1 square centimeter on the paper represents 0.25 actually, because if you square this one, is going to give you 0.25 square kilometers. But here remember we have 20.5 square centimeters. So what we should do here is to convert the 2 measurement into an equivalent measurement. If 1 square centimeter on the paper represents 0.25 kilometers on the actual ground, then what about 20.5? So we shall take 20.5 square centimeters, and then we find its equivalent here. And if we do so, we are going to get 20.5 multiplied by 0.25 kilometers, square kilometers over 1 square centimeter. We will find that one cancels, and we shall have 5.1. We are going to get the area as 5.125 square kilometers. And that is how we can approximate the area of a given figure or a given area using the counting technique. As we have seen, you set it to a great square. we are going to see another section whereby we are going to approximate a given area or of a curve by a trapezium rule or method. Let's see part of it, and we can say that generally if you are being given any kind of a curve, we divide the area under the curve into different kinds of trapeziums, of which we then approximate the area of that given trapeziums, and then we sum them all up. Then on approximating using this trapezium, what we usually make sure is that the base of it, which is known as the height or h, it should always be equal. For instance, let's say this is our our curve of x squared plus 2x plus 1. And then we are being told to find the area under the curve, where this is the y-axis, this is the x-axis, between these lines. Let's say maybe the area under the curve is this area. We can be asked to find the area under the curve of the shaded area as shown below. So what we normally do is this: we find the number of strips, meaning we divide the area under the curve into strips of trapezium, and we can decide to divide it first at that point. Sorry. We can divide it into that way. Then the distance from here to here, this distance should be the same. This distance should be the same. And as we know, if we divide this one as in trapezium, for example, that one to be our trapezium, that one we assume is a perfect trapezium, but we divide it in that way, as according to my curve gives me almost a perfect trapezium, but sometimes it may be in a zigzag way, but we still divide it this way. But the more you put h to be smaller, or the smaller the size of the trapezium, the accurate the answer you will get. Thus, we can find it better by taking the area of there, whereby, for example, if this one is given y1, this is y2, y3, y4, y5, then y7 and y8. If you want to approximate the area of this given figure, what we normally do here is that we first find the given condition. And here you may just be told to find the area under the curve from x equals to 0 up to here, of which it may be x equals to k. For example, ours is from x equals to 0 at this point, then to x equals to k. You may be given conditions. If you have been given condition, you use that condition to help you divide your given area into the required number of strips of which you will manage. Sometimes you may be given a condition that you should divide them into a required number of strips. What you should do, you find the distance between them, then you divide them with the number of strips you require and find how much should h measure. If that is the case, for our instance here, we are having that the distance from x-axis to the curve with regarding to y, we will find the first one y1, the second one is y2, third y3, fourth, fifth, up to seventh, up to the last one, which is the 8th for our case, as y8. And we can say that to find the area of each trapezium, we understand it from the previously, at form 3 actually, we said to find the area of the trapezium, we said it will be y, the trapezium area, it will be a half. It is normally a half height, you multiply by the height, then one of the smaller side plus the other bigger side. You add the two sides which are parallel to each other. After adding the two sides which are parallel to each other, or not parallel but it's a trapezium, then you multiply by the height between them, but the lines must be parallel. So, meaning that if we do that, we are going to have our h here, which we refer to as height, is the uniform distance between the two, between the, or among the y's, among the trapeziums. So the distance among them, the equal distance is what we are referring to, our height. And AB is referring to the distance from x-axis up to where the trapezium touches the curve. For instance, if we need the area of this trapezium, if we want to sum them, for instance, if we need the area of the first trapezium, it will be a half multiplied by the h, which is the distance from this point to that point. And then we multiply by y1 plus y2. That are the A and B. Then we cross the bracket. So this one is going to give us h over 2 into y1 plus y2. And that is what we are going to find. Then to the next, if we need for the next, it will be area of the next is going to give us h over 2, because the same procedure there, but what only changes is that the y1 of 2 is y2. This is trapezium 1. Let me name them. Trapezium 1, 2, 3, 4, 5, 6, 7. So the area of trapezium 2, it will be, this is for 1. So for 2, it will be h over 2, y2 plus y3. If it is for 4, area of trapezium 3, let's say 3, it will be h over 2, which is the difference here, height, which is equivalent, multiplied by y3 plus y4. As this continues, you will find that it will be moving that way until to the final y. So, in conclusion, we can find the area there by saying it will be the area of the total the curve. We will find it as area equals to h over 2 into y1 plus y2 plus h over 2 into y2 plus y3 plus h over 2 into y3 plus y4 plus h over 2 y4 plus y5 plus h over 2, actually this is h, y5 plus y6 plus h over 2 y6 plus y7 plus h over 2 y7 plus y8. And we find that's the final place. And from there we can now sum them together, and we shall find that if we need to find the area of that trapezium, if we collect them together, we are seeing that h over 2 is uniform. And remember, h we say is the uniform distance between the two, between the one trapezium to another. That is the h. So it will be h over 2 into, now we have y1 plus y2 plus y2 plus, let me write y1 plus y2 plus y2 plus y3 plus y3 plus y4 plus y4 plus y5 plus y5 plus y6 plus y6 plus y7 plus y7 plus y8. That is the final. Y8 is the final one. And if you may view well, you will find that only the first one and the last one are not repeated, but the others are repeated. So that means that we can say h over 2 into, actually let me put them into a special bracket, y1 plus y2 plus y8, because they are not repeated. Then I take those which are being repeated because they are twice. Then I will say it is y2 plus y3 plus y4 plus y5 plus y6 plus y7. If I do that way, I will have find the area of the area under the curve of this whole trapezium, and that one will give me an approximation of the area using the trapezium rule. This is the trapezium rule we need. We should handle one of the example here. One, let's say estimate the area bounded by the curve y equals to a half x squared plus 5. So we need to estimate the area bounded by the graph y equals to a half squared plus 5, but condition is the x-axis bounded by the curve with the x-axis, and the line x equals to 1. Line should be x equals to 1 and x equals to 5. X equals to 5. So we are just using trapezium rule. So we have been just informed to estimate the area bounded by the curve y equals to a half x squared plus 5 with the x-axis and with the line x equals to 1 and x equals to 5 using the trapezium rule. What we should just find here is first find how we can plot that graph, and we say if this one is x, then what should we get as y? So if we put here 0, we shall find this will be 5. If it is, let me, for example, here from 1, we have been given 1 to 5. So it will be 1, 2, 3, 4, up to 5. And we shall find that for 1, here we are going to have 5.5. And if we place 2 there, we are going to have 7. 3 will give us 9 over 2, that is 4.5 plus 5, 9.5. 4 going to give us 16, 8 plus 5, that is 13. Then 5, 25, divided by 2, 12.5, add that one, 27.5. 17.5 actually, not 27. That is 5 squared, 25 over 2, 12, 17.5. So on doing that, we can now draw the graph as this way. Because it's starting from 0, we can estimate our 0 as that point. Then we say let this one be 0 here. So 1, 2, 3, 4, 5, 6. Then the other part, we can take it to be let's type 5, 10. It's up to 17, so 5, 10, 15, then 25, and 15, 20. We can estimate using that. So if it's 0, we are having it at 5. And then 1, 1.5, we shall have 1, 1.5, or 1, 5.5, so it's somewhere here. And 5.5 is somewhere there. 2, 7, let's say it is somewhere here, approximation. And then 3, 9.5, 3 nearly to 10, so 3, 9.5 will be there. 413 is going to be somewhere here. And then 5, 17.5. 5, 17.5 is going to be somewhere here. So if we plot the curve, we are going to find that our curve is almost passing through that point. So we need to find the area under the curve from x equals to 1 and x equals to 5. So if it is from x equals to 1, it means we shall start with this x equals to 1. Actually, let me change so it may be well visible. It's from x equals to 1, this one. That will be our y1. And then the final one is x equals to 5, and it is here. That is our x equals to 5. So the area which we need to find is the area under this curve. And we have been told to find it using trapezium rule. Here what we shall do, we can divide it into equal number of strips, and the number of strips should have the equal base measurement, of which we can decide let it be divided in these kinds, so that we may arrive up with 1, 2, 3, 4 strips of 1 unit each. So if we do that one, we are having 4, but each have 1 unit each. So from the formula we can say we are having the first one as x equals to 1, and the last y is x equals to 5. So what we shall do is this. We shall first find if x equals to 1, what does we have our y as? We shall find our y is equivalent to 5.5. And if it's 2, we found this one is approximate to 7. And if it's 3, we said it's approximate to 9.5. And this one will give us 13. And this is 17.5 as our y. So meaning we can still find our area of the trapezium by saying that it will be now h over 2 into, first we said those which does not repeat, which is y1 and y2. So it will be that of x1. So our h, we said it will be 1. It is 1. So 1 over 2 remains 1 over 2. And then y1 is 5.5 plus the last y is 17.5. Then we add to 2 into those which should be repeated is 7 plus y3, which is 9.5. Plus 13. Let's see what do we find here. So what we are finding for the first bracket, if we work out 5.5 plus 17.5, we are getting 23. For the first bracket is 23. And here 7 plus 9.5 plus 13, we are getting 29. So if you multiply by 2, it is giving us 59. This all is giving us 59. So meaning we take 23 plus 59, so the total will be a half into 23 plus 59, and we are going to get 82. So that is divided by 2, it's giving us 41 square what? Square unit. We have seen how we can approximate the given area using trapezium rule under the curve. And we have used one of ours, which was y equals to a half x squared plus 5. And we have seen we can use it with x equals to 1 and x equals to 5 using the formula of trapezium rule to estimate the area by using the appropriate values of y and that of the base measurement. And we have found for our case is 41 square unit. We are going to learn about these mid-ordinate rules, and we are going to use it to approximate area of given irregular or curves, the area under the curves, using the mid-ordinate rule. And we can say that the mid-ordinate rule is whereby we divide the given area under the curve into straight rectangles which may be above or less than, but they may be compensating to each other in a circular way in a given curve. So we shall see it as we can do it as we progress on. For instance, if we have been given, for example, a kind of an area, the first thing you should do after being given a kind of an area, for example, if it's this one, let's take an area as this part. So you divide each strip with the same, let's say this one to be h. You divide it with the same length. The length from this point to the other should be always equal, as it was in trapezium rule. Then, after dividing, before you divide, the first thing you should do is know how long is the base. After knowing how long is the base, if this is our x-axis and this is y, you should understand how long is our base. After knowing how long the base is, you divide it using the number of strips you require. The number of strips I'm referring to this. This one is the first strip, second, third, fourth, fifth, sixth, seventh. Those are the number of strips we require. So like mine, I divided it into 7 strips, giving me with the h height. Then I will identify the mid-ordinate. I will draw a vertical from where the line is meeting here. Let's say that is my first vertical line, and this one will be my y1. You draw a vertical line. For example, if it is here, you draw a vertical line where the 2 is compensating. The best one should be like this. It is above and also below the curve. That is the best rectangular to be drawn. After drawing that one, then you draw a line which touches the mid-ordinate line should touch the place where the rectangle cuts the curve. At that point is where you should draw your vertical line, and it should touch your base. And after getting that, you continue with the others up to the end. You find your head, your y's. After finding your y's, for instance, like mine here, let's say this 1, 2, 3, 4, 5, 6, 7. If you have drawn it like this shape, if the curve was that smooth, you will find that it should look like this. It should always be in such a way that if the curve passes this way, the line is always compensating. It is up, the rectangle is both up, covering the both up space and also the down space, so that the area of this one should compensate the area of the other part, such that the line drawn inside the dotted line, which is a vertical line touching here, this line which will touch here, is what I'm referring to as the vertical line, or is specially known as mid-ordinate line. That is what we refer to as mid-ordinate line. After drawing that one, that is the line which we refer or we assign as our y1 as we proceed. After getting that one now, we can find the area of the curve by taking y1 multiplied the change in equivalent sizes. So like for example, if I need the area of here, I will take h multiplied by y1, because it's a rectangle anyway, so it will be h multiplied by the length, which is h by length y1. Then I add to h by y2. Then I add to h by y3. I add to h by y4. As the process continues, if it's up to 7, it will be h plus y5, and then plus h by y6. 6 plus h by y7. That's the last one. And we have found that each of the measurement here we will be finding is the area of the given rectangle using the mediordinate as the length of that rectangle. So after doing that, we shall find that h is common in both of them. So you will find that you are going to have hy1 plus hy2 plus hy3 plus hy4 plus hy5 plus hy6 plus hy7. And we can see that in both of them h is common. So what we should do is that we should factor out h, and we shall find is h1 plus y2 y3 plus y4 plus y5 plus y6 plus y7 for our instance, and this one will go on up to the number of y's you will be having. And remember, y here is representing the mediordinate which you have, the vertical line which was touching at where the balancing was taking place here. This is what I'm referring to. The line which was drawn from this point up to the base, that is my mediordinate. Now we are going to observe an example using the mediordinate rule, as we have seen how we may find the area using the approximation using this method. Now we have been told estimate the area of a semicircle of radius 4 cm using mediordinate rule with 4 equal strips, each of width 2 cm. Now you have been told it is of radius 4 cm. So what we do here, you will find if you draw that as our to be our semicircle that way, you will find the distance from this point to the other point is 4 cm as we have been given. So meaning the diameter will be 8. Then we have been told to find each strip we should have 2 cm. So meaning that if each strip is having 4 cm and this one is 2 cm, this one is 8. So what we should do here, we should calculate how many strips should we have. Our total distance it is 8 centimeters. And each strip should contain 2 centimeters. How many strips should we have? If you do that way, you are going to find we should have 4 number of strips. So after 2 centimeters, we are having a strip. After 2 centimeters, we are going to have a strip. For instance, if it is here, you will find that at the middle of it, we are going to have a strip here. That is at 2 centimeters. This is, after this one, this is 2 centimeters. This is 2 centimeters. The same applies to this. This one is 2 centimeters. The same to this. It is not drawn to scale, but if drawn to scale, well, it will well be identified. So having that one, we can say, if you draw it using the best method of a scale measurement, you will find that the first one is rising up to 2.6 using a graph. This one is up to 2.6, and the middle one, actually, let me draw this line. Well, these are the strips. Now, we need now, if it is a graph, you will, after doing that, you will have to take the mediordinate of this one, and you will find it will be, for example, that way, which will cut both out and in. If this one is drawn to a graph, you will find it is cutting that way. This one is also cutting the same thing. This one is up to that point, and then from there we are going to have another one here. Another one will be here. Another one will be here. So we are going to have that one. And the first medianate we are finding it to be 2.6. If you use a good graph, you should help me use that one. You will find it's 2.6. And another one is giving us 3.9. This one gives 3.9. This one too, 3.9. And the last one is also 2.6. Remember, it's a semicircle of 4 centimeters radius. So meaning these things are just alternating itself. So 2.6. Now we can use by this one, we can refer, if this is y-axis and this one is moving along the x-axis, we can say that this will be our y1, this one y2, y3, and y4. So after doing that, we shall find now, we will find that, after doing that, we will find, using our formula of h equals to the number of y's we have, then we shall start, we have, how many y's do we have here? We have 4. So it will be y1 plus y2 plus y3 plus y4. But here, h we have here, h we found is 2. We were told should be of width 2 centimeters. And then, the first y we found is 2.6. The second one was 3.9. Third, 3.9. The fourth was 2.6. On adding them together, we shall find 2.6 plus 3.9 plus 3.9 plus 2.6. We are going to have something like 13. So if we get 13, but remember this 13, we have 2 outside. So after multiplying by 2, we are going to have something like 26 square unit. We said using the two methods, that is Ordinate Rule and Trapezium rule, we said they are only used to approximate the area of a given figure or a given region, let's say, like that. So they are only approximation method ways. So we can still find the actual area of this semicircle. We have found using that method, we find it to be that way, but we can find the exact. And the exact, we can find it by taking a half. It is normally a half by r squared, whereby a half is being represented by, it is a semicircle, so it's 180 degrees over 360, so it will give us a half, multiplied by 3.142, multiplied by the radius is 4 centimeters, so it's 4 by 4, and we get 3.142 by 0.5, we get it's giving us 25.136 square centimeter. This is the exact area, but we can find that our area here was approximately equal to this. So meaning our approximation method is almost right. So that is how we conclude it. And we say that using this method doesn't guarantee to give us the correct or the accurate answer, but it only gives us an answer which is approximately to what we are seeking. So the methods are just there to help us approximate the area of given objects using those methods. Thank you for watching. Stay tuned for our next videos.